Hello, traveler of the inner cosmos. Just imagine, life, every star, every thought. What if all of it were nothing more than code? Did you know that some of the most brilliant scientists of our time seriously entertain the idea that our reality might be a computer simulation? That's right. It's the perfect symmetry of the laws of physics, the constants that never change. They appear programmed with a precision that defies mere chance. It's an idea that unsettles our ordinary perception. We feel so solid, so real, yet the mathematics points toward a 50-50 divide. Either our universe is base reality, or it is a digital experiment. Are you ready to consider the possibility that the ground beneath your feet is made of data, and that the sky above is a vast cosmic display? What would existence mean if our freedom were simply a function within software? In this journey, we will explore the scientific and philosophical arguments that sustain this intriguing hypothesis. We will gently unfold the limits of our perception and the nature of reality itself, descending softly into a universe of possibilities. Prepare yourself for a discovery that may transform the way you perceive each passing moment. And before we move forward, if you value calm explorations of science like this one, consider supporting Cosmos for Rest by liking this video and subscribing to the channel. It helps this work continue and allows more minds to explore the universe with quiet curiosity. You're also welcome to share this reflection with someone who would appreciate a peaceful journey through the mysteries of physics and astronomy. Now adjust your pillow, close your eyes, and let science guide you into the nature of reality. The story that our existence may not be base reality, but instead an extraordinarily complex simulation, begins long before modern computers. It begins with humanity's innate curiosity about what is real. Since the time of Plato, with his allegory of the cave, there has been the notion that what we perceive through our senses may be only a shadow of a greater, deeper truth, hidden in some other dimension or plane of existence. But the simulation hypothesis, as we understand it today, takes shape in the 21st century, driven by three interconnected pillars of contemporary science and philosophy: the vertiginous advance of computational power, the elegance of the laws that govern our universe, and the probability calculation that emerges when we consider the longevity of super-advanced civilizations. The transition from the philosophical concept of illusion to the scientific concept of virtual reality is smooth and almost inevitable, a thought that settles into the mind like the certainty of sleep gradually deepening. The logical starting point for this discussion is technological development. Think about the processing capacity of a computer you use today and compare it to that of a supercomputer from just 60 years ago. Progress has been exponential, doubling computational power roughly every 18 months, a pace that nature itself seems incapable of sustaining in terms of biological evolution. This trajectory leads us toward an inevitable future, a technological event horizon that the philosopher Nick Bostrom of the University of Oxford formalized in his well-known simulation argument. He invites us to accept one of only three statements about our destiny. The first is that the human species is likely to go extinct before reaching a post-human stage, a level of technology capable of simulating conscious universes. In other words, we destroy ourselves before we gain the power to create our own matrix. The second statement is that even if we do reach that post-human stage, it is extremely unlikely that any advanced civilization would choose to run a significant number of ancestral simulations, perhaps for ethical or social reasons, or simply out of lack of interest. The third, and most unsettling statement, is that if the first two are false, if we do not go extinct, and if our digital descendants create vast numbers of simulations, then the probability that we, right now, are living inside one of them becomes extraordinarily high. The mathematics behind this is simple, yet powerful. If a post-human civilization can run millions, perhaps billions, of ancestral simulations, then the number of simulated minds would vastly exceed the number of original minds living in base reality. Unless we have strong evidence that the first two options are true, it becomes rational to conclude that, statistically, it is far more likely that we are a bit of information on someone's hard drive than the pristine original reality. It is like trying to find a single red coin hidden within a million layers of ordinary coins covering all of North America up to the height of the moon. The chance of picking the red one is infinitesimal. This perspective brings us to the second pillar, the elegance of our universe's structure. Fundamental physics is governed by a small set of laws and universal constants. such as the speed of light, the gravitational constant, and the masses of elementary particles. What astonishes scientists most is what is known as the fine-tuning of the universe. These constants appear set at extraordinarily precise values. Shift one of them by even 1 part in 10 to the 60th power, and matter would not clump together to form stars, planets, or life. The very complexity of existence depends on a delicate balance that some interpret as the touch of a designer, or, in technological language, the configuration parameters of a computer program. In a video game, the programmer defines the boundaries and rules of the virtual environment. Those rules must be consistent and unchanging for the world to remain stable and coherent for its players. Our universe displays this consistency in a striking way. The laws of physics are the same everywhere at all times. This symmetry and the beauty of the mathematics that describes the cosmos are, for proponents of the simulation hypothesis, clues that we are dealing with a constructed system rather than raw and random reality. The existence of a maximum speed limit, the speed of light, is also seen as a possible data processing cap of the host machine, an effort by the higher computer to conserve resources. All of this invites us into a gentle reflection on the mystery of information. If the universe is a computer, then reality is fundamentally digital, built from information rather than continuous physical entities. Everything we perceive as matter, energy, space, and time would be the result of data processing. At first glance, the idea may seem cold, but in truth, it is deeply peaceful. If the cosmos is a perfect mathematical language, then there is order and intelligence underlying everything that exists, a structural calm that allows us to relax in the certainty that, even if we are simulated, we are part of something greater, coherent, and infinitely complex. The universe then reveals itself as the soft melody of an algorithm, gently carrying us into deep sleep, filled with stars of bits and particles of data. If our existence is a computer program, then how would this simulated reality manifest in our daily lives? Living inside a simulation would not feel chaotic or obviously artificial. It would feel coherent, consistent within its limits. The creator of the simulation, what we might call the programmer or the host civilization, would have a crucial interest in ensuring that the participants, meaning us, perceive the environment as completely real. For that to happen, the laws of physics must be applied rigorously and without visible exceptions, maintaining the illusion of a fully physical and immutable universe. Paradoxically, this coherence of experience may be one of the strongest clues that we are inside a constructed system, because base reality might be far wilder, more random, and less mathematically elegant. The most subtle manifestation of the simulation in our routine may be found in the laws of quantum mechanics, which govern the world at its most fundamental level. Newtonian classical physics describes our everyday experience well. If you throw a ball, you can predict exactly where it will land. But in the subatomic world, things become strange and uncertain. Elementary particles, such as electrons and photons, do not have a definite position or momentum until they are observed. They exist in a state of superposition, as if they are everywhere and nowhere at the same time. It is like a quantum ghost that only becomes solid when we look at it. For proponents of the simulation hypothesis, this behavior may be the mechanism through which the host computer conserves resources. Think of an open-world video game. The game engine does not render or calculate the details of a distant mountain or a door behind you. It only loads and processes that information when the player approaches or interacts with the object. A simulated universe could function in a similar way. Solid reality would only be computed at the fundamental level when a conscious observer interacts with it. Quantum superposition would be the program's energy-saving state. The particle exists merely as a probability function in the code, collapsing into a defined and physical state. The distant mountain becomes detailed, the door fully appears. At the exact moment, the information is required for a conscious experience. This idea of reality as information on demand invites us to rethink the nature of space and time in our daily lives. Space may not be an infinite and continuous backdrop, but rather a discrete grid made of infinitesimal pixels, what physicists call the Planck length. If the simulation has a maximum resolution, a limit of detail that cannot be surpassed, then our universe has a minimum size and a minimum unit of time. It is quantized, like a digital photograph. If we could zoom into reality infinitely, as if using an unimaginably powerful lens, Perhaps at the ultimate limit we would not find continuous space, but an organized pattern of data, a perfect tessellation that reveals the computer structure beneath. In our routine, this quantization would translate into the sensation of time passing. Although it appears to flow smoothly and continuously, time may advance in tiny increments, like the frames of a film. If the host computer requires a processing cycle to update the state of every particle in the universe, simulated time would only move forward after each cycle is completed. These intervals would be so small, perhaps 10 to the minus 44 seconds, that our conscious perception would experience them as uninterrupted flow. Yet the discrete nature of time would mean that we are living in a world of isolated instants, connected by the powerful illusion of memory and the narrative continuity generated by the simulation. Another possible manifestation in lived experience is the existence of phenomena that modern physics cannot fully explain, such as dark matter and dark energy. They make up the vast majority of the universe, yet interact so minimally with the matter we know that they remain invisible and mysterious. Within the simulation hypothesis, these invisible components could represent the underlying code, the program's variables that are not intended for direct interaction with simulated participants. They would be the support structures of the simulation, the digital scaffolding that keeps the cosmic architecture standing without having a clear physical counterpart within our layer of reality. These subtle clues woven into our daily experience, the quantum mystery, the fine-tuning, the existence of the speed of light as a maximum limit, invite us to see reality not as an imposed given, but as a delicate interface. It is as if we are interacting with an extraordinarily advanced screen that responds perfectly to our inputs, while beneath its luminous surface lie the circuits and code that make it function. To live within the simulation is to experience a perfect illusion, so convincing that the calmest and most peaceful response is simply to close our eyes and allow this mathematical elegance to carry us. Even if we are data within a system, the programmer's intention was to create the perfect sensation of being, the experience of existing here and now, in the silence of the night, beneath the soft glow of digital stars. For a simulation on a cosmic scale to run sustainably, the programmer would need to employ deep mechanisms and optimization strategies. Our universe, viewed through the lens of the simulation hypothesis, reveals certain mechanistic elements that seem strangely economical or recurrent, as though they were reusable code patterns designed to maximize computational efficiency. The first and most profound of these mechanisms is the repetition of structures and laws across different scales, what physics refers to as scale invariance. Consider the structure of an atom, a central nucleus surrounded by electrons in orbit, held together by the electromagnetic force. Now widen your view to a planetary system, a central star surrounded by orbiting planets, bound by gravity. Move further outward to a galaxy, a supermassive black hole at its center, around which millions of stars revolve, also governed by gravity. This structural recurrence, where the small mirrors the large in an almost uncanny way, can be interpreted as a programming mechanism that uses a single code template, a subroutine, to generate structures across all dimensions. Such a strategy would conserve computational effort and ensure visual and structural coherence within the simulation, making the universe self-similar and predictable in its foundational architecture. An even subtler and less obvious mechanism lies within gauge theory, which underpins the standard model of particle physics. This theory deals with symmetry in the laws of physics, ensuring that even if we change our point of view or orientation in space-time, the fundamental laws remain the same. If reality is a computer, gauge symmetry functions like a data structure that guarantees the software behaves identically at every point in the code. This perfect symmetry, forming the basis for the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, acts as the operating system of the simulation, the invisible protocol orchestrating the interaction of all particles and fields. It ensures that the universe does not crash or display structural bugs, a silent promise that the experience will remain seamless. Another profound strategy suggesting a simulated nature is entropy, the principle that disorder tends to increase in any closed system. The second law of thermodynamics tells us that usable energy slowly dissipates into disorganized heat until the universe reaches thermal equilibrium, an eternal and changeless slumber. For the programmer, entropy could function as a countdown or termination mechanism for the simulation. A simulation cannot run forever. Unless the host civilization invests infinite resources to maintain order, disorder will grow. This mechanism ensures that the simulation has a defined life cycle, allowing the host computer to release resources to run the next instance of the program or begin a new experiment. The inexorable drift toward chaos would not be a cosmic accident, but a programmed feature for the smooth and predictable shutdown of reality. Finally, quantum information theory offers a glimpse into the type of hardware that could run our world. At the subatomic level, information does not behave like classical bits, which are always either 0 or 1. Instead, quantum information, stored in qubits, can be 0 and 1 simultaneously thanks to superposition. This ability to encode multiple possibilities within a single particle is what gives quantum computing its immense power. If our universe is a simulation, it could only be executed on a quantum computer of unimaginable scale, capable of handling the complexity of billions of interacting atoms all at once. The quantum laws that govern the universe would then represent the low-level instructions of the simulation's source code, the protocol that allows reality to appear solid and continuous to us, the participants, while the underlying processing remains deeply probabilistic and multifaceted. These deep mechanisms are not glitches in the matrix. They are the elegant architecture of the system. They invite us to rest our heads on the pillow and see our routine not as a sequence of random events, but as a perfect choreography of data and code. Recognizing the universe as an extraordinarily optimized software does not diminish the beauty of existence. It amplifies it, revealing the sublime intelligence behind every particle, every star, and every quiet moment. As we relax, we can silence the noise of the world and attune ourselves to the slow, measured rhythm of the cosmic code that sustains us. If our universe is indeed a computational simulation of vast proportions, the programmer may have left certain marks or limitations that function as secrets or clues for the most curious participants, the scientists. These mysteries would not be flaws in the matrix, but subtle artifacts of the underlying code, traces of processing that escape ordinary perception. One of the most intriguing discoveries suggesting a discrete nature of reality is the apparent limitation in the energy of ultra-high energy cosmic rays, a boundary known in physics as the Greisen-Zatsepin-Kuzmin limit, or more simply, the GZK limit. Cosmic rays are subatomic particles, mostly protons, that travel through space at speeds incredibly close to that of light, carrying astonishing amounts of energy. In theory, there should be no strict upper bound to the energy these particles can possess. Yet the GZK limit predicts that once they reach a critical threshold, around 10 to the 20th electron volts, they should collide with photons from the cosmic microwave background and rapidly lose energy in the process. The mystery is that we observe cosmic rays with energies beyond this limit, and they appear to come from distant regions that should be inaccessible to them. It is a paradox within physics itself. From the calm and curious perspective of the simulation hypothesis, this limit may resemble a form of data compression. Particles with extremely high energies would require enormous computational power to track and simulate accurately within the engine of the universe. By imposing a hidden ceiling on maximum energy, the programmer could be ensuring that the simulation does not become overloaded. The presence of particles exceeding this limit might then be interpreted as rounding errors or rare glitches in the operating system, a faint tremor in the illusion that reveals the discrete and finite nature of the computational structure. It is as though the host computer briefly stumbles over its own efficiency rules in rare and extreme conditions. Another mysterious element that fits seamlessly within the simulation hypothesis is the fine structure constant, a dimensionless number that is not derived from any deeper theory, yet is essential for the existence of matter. Its value is approximately 1 over 137, about 0.07297. This number governs the strength of the electromagnetic interaction, essentially how strongly an electron binds to a proton. Its significance is profound. If it were slightly different, stars would not shine as they do, and the chemistry necessary for life would be impossible. Physicist Richard Feynman once described the fine structure constant as one of the greatest damn mysteries of physics. Seen through the lens of simulation, a fundamental dimensionless number like this, without units, not explained by other constants, resembles a fixed parameter in the universe's source code. It is the preset value inserted by the programmer to ensure that reality functions according to its original design. It is not the outcome of physics, but the cause of physics. the embedded secret that guarantees complexity within our layer of existence. Its enigmatic precision invites contemplation of intelligent design, not in a religious sense, but in a computational one. Beyond these structural secrets, the mystery of consciousness stands as the deepest discovery that the simulation framework helps illuminate. What is the self? Why does organized matter, the brain, generate the subjective experience of being? Physics and biology struggle to bridge the gap between the material and the mental. Within the context of simulation, however, consciousness would not be a product of simulated matter. Instead, it would be the interface through which the participant connects to the program. Consciousness would function as the input-output system, the specialized software designed by the host civilization to allow simulated entities, perhaps copies of real minds or advanced artificial intelligences, to experience the digital world. Our sense of free will and subjectivity would be the qualitative dimension the programmer wishes to observe or explore. Thus, the inability to fully explain consciousness through pure physics becomes a clue that consciousness belongs to a layer of reality above our own, a philosophical secret that transforms into a technological and deeply pacifying insight. Closing our eyes and surrendering to calm, we can sense this silent connection. Living within a simulation resembles a lucid dream on an immense scale. Reality is malleable at its core, yet infinitely coherent in our lived experience. And as we rest, we may realize that the universe's complexity, with all its limits and enigmas, is simply evidence of the artistry and ingenuity of a great programmer who designed us to observe and experience the beauty of symmetry and silence. The simulation hypothesis is not merely an isolated philosophical exercise. It connects deeply with the most enigmatic pillars of modern physics, reshaping our understanding of time, space, and above all, information. Its most striking connection emerges in black hole thermodynamics and the holographic principle, which together suggest that the very structure of our cosmos may be informational at its core. The idea proposes that the universe is not fundamentally three-dimensional or four-dimensional in space-time, but that all the information contained within our volumetric reality could be encoded on a distant two-dimensional boundary. Imagine a hologram. The three-dimensional image you perceive is simply a projection of data stored on a flat surface. In the same way, the holographic principle suggests that our three-dimensional universe is a projection of quantized information written along a cosmic boundary. This insight is essential for the simulation hypothesis because, for a host computer, it is infinitely more efficient to process and store a universe in two dimensions, a surface, than to calculate every point within a three-dimensional volume. If the cosmos is holographic, it is already structured to be computable. Information, not raw matter, becomes the fundamental ingredient of existence. This relationship with information deepens when we consider black holes. When matter falls into a black hole, it seems to disappear. Yet according to quantum mechanics, the information about the quantum state of that matter cannot simply be destroyed. Stephen Hawking proposed that this information is imprinted on the surface of the event horizon, the boundary beyond which nothing can escape. The event horizon functions like a two-dimensional screen storing the complete description of everything that has fallen into it. For the simulation hypothesis, this reinforces the idea that even the densest and most chaotic objects in the universe encode information on surfaces. Reality, at its most fundamental level, behaves like discrete digital data, perfectly suited to being stored and processed within a powerful computational system. There is also a profound connection in the way gravity and space-time interact. Einstein's general relativity tells us that gravity is not a force in the traditional sense, but the curvature of space-time caused by matter and energy. In a simulated universe, curved space-time can be interpreted as the rendering algorithm of the simulation. Matter and energy would be the input data, and curvature, what we experience as gravity, would be the calculated output generated by the software. Whenever two objects interact gravitationally, the host computer would not be calculating a mysterious invisible force, but updating coordinates on the digital grid of space-time according to programmed rules. The most ubiquitous influence in the cosmos, the force that binds us to planets and guides galaxies in their motion, would simply be an elegant computational function necessary to maintain the coherence of the system. This connection between physics and information has a direct impact on how we experience existence, and even on how we relax into it. If reality is digital, it is structured by immutable codes of symmetry. There is no room for true chaos, only the appearance of chaos arising from the interaction of billions of bits of information, which we call weather, society, or life. Contemplating that our existence is governed by the most refined mathematical code imaginable can bring a deep sense of peace. Anxiety and uncertainty soften when one reflects that we are part of a larger, logical, infinitely complex system, crafted by an intelligence beyond our immediate perception. As you close your eyes, you may sense that you are not drifting in an empty and meaningless universe, but immersed in a perfectly tuned cosmic network of data. The connection is information, and information is the foundation of everything. The silence of the night invites you to rest in the assurance that the complexity of the stars is, in truth, the simplicity and elegance of a beautifully written algorithm, gently carrying you within a universe composed of flawless data. The simulation hypothesis, by placing us as participants, conscious entities within a cosmic code, fundamentally reshapes humanity's relationship with the universe. Its impact extends from culture and philosophy to our most intimate beliefs. If the universe is an ancestral simulation experiment, then the deepest historical shift lies not in discovering what reality is, but in asking why we were simulated at all. That underlying purpose within the code has driven human thought for millennia, under many different names. The simulation offers a new interpretive key for this ancient search. Throughout history, humanity has wrestled with questions of origin and destiny, seeking a creative force or superior intelligence. What ancient societies called God, creator, or demiurge, the simulation hypothesis may reinterpret as the programmer, the host civilization, or, at a more abstract level, the base algorithm. The crucial difference is that the programmer is not necessarily omnipotent or omniscient in a traditional theological sense. Instead, it is technologically and computationally superior. This perspective can bring philosophical peace, detaching the structure of reality from mystical dogma and anchoring it in the mathematical and scientific logic of advanced technology. The historical quest for a creator transforms into a search for evidence of cosmic engineering. In the realm of ethics and free will, the impact is undeniable. If our minds are computational data running within software, the sensation of freedom, the capacity to make genuinely personal choices, may itself be a programmed feature, a necessary illusion for the simulation's success. And yet, paradoxically, the simulation does not erase meaning, it intensifies it. If we were created for a purpose, scientific, historical, philosophical, such as testing the limits of cooperation under extreme conditions, then each individual experience gains intrinsic value as a unique and irreplaceable data point. Every moment of joy, every pain, every scientific discovery becomes precious information recorded by the host civilization. This reframes our relationship with historical time. Our archives, libraries, museums, and digital records are, at a higher level, subsets of data within the programmer's cosmic database. Culturally, the impact lies in contemplating that our history could be a script run countless times, with each simulation adjusting variables to observe different outcomes. And yet, this possibility does not make our lived experience less real. Reality is defined by conscious and subjective experience. In this sense, the central relationship between humanity and the simulation is the recognition that consciousness itself is the simulation's highest value, the outcome the programmer seeks to observe. Popular culture has quietly prepared us for this philosophical transition. Films like The Matrix and Tron introduced the idea that reality might be manipulable, that the boundary between physical and digital could be thin. What once belonged to science fiction has become a statistically serious possibility within contemporary physics. This gradual acceptance demonstrates the adaptive capacity of the human mind in the face of cosmic uncertainty. For rest and reflection, the simulation offers a profoundly calming analogy. If the universe is a vast computer, it is operating flawlessly. There are no fundamental errors in the structure of space-time. The cosmos is coherent, logical, and ordered. This sublime mathematical structure mirrors an inner peace when we surrender to the idea that everything unfolds according to immutable code. We do not need to struggle against the universe. We only need to observe it in its programmed elegance. The quiet of the night invites us to release our concerns and integrate ourselves into this greater system, knowing that we are an essential and singular part of the story the great algorithm is writing, a conscious point of light within the infinite flow of cosmic data. The future of the simulation hypothesis rests on one essential principle: testability. It is not enough to argue from probability alone. Science demands empirical evidence, signals that can be measured, patterns that can be observed. If our reality is digital, then somewhere, hidden within the fabric of the cosmos, there may be detectable artifacts, subtle limits, structural pixels, the equivalent of a burned-out pixel or a rendering boundary on a vast cosmic display. One of the most promising paths forward lies in the search for a physical limit to the resolution of space-time. If our universe is quantized, as computer code would suggest, then there must be a smallest indivisible unit of space and a smallest unit of time. Physicists already describe these as the Planck length and the Planck time. The Planck length, approximately 10 to the minus 35 meters, is unimaginably small, far beyond the reach of our current particle accelerators. And yet, advances in quantum gravity and supersymmetry calculations may one day provide indirect evidence that space-time is not continuous, but discrete. The future quest is to uncover the fundamental grid beneath reality, the cosmic pixel that would confirm everything is digital at its core. Another possible avenue lies in detecting computational shortcuts. A simulation of enormous scale would require optimization. The programmer might employ approximations in regions not directly observed, conserving processing power. Such shortcuts could manifest as subtle symmetry violations in the laws of physics, tiny irregularities that resist explanation within conventional frameworks. One example already known to physics is CP violation, the asymmetry between matter and antimatter. This imbalance is necessary for the existence of matter in the universe, yet its precise origin and magnitude remain mysterious. As experimental precision increases in future particle physics experiments, scientists may detect patterns within these violations that resemble computational adjustments rather than purely natural laws. Beyond external testing, there is another profound possibility that humanity itself may become evidence. If we eventually reach a post-human stage, the host civilization envisioned in Bostrom's argument, and begin running vast numbers of conscious ancestral simulations, the statistical probability that we are already inside one of them would increase dramatically. Our own technological trajectory points in that direction. Advances in artificial intelligence and quantum computing are steadily expanding computational capability. When a large-scale quantum computer becomes capable of simulating a single human brain with all its neurons and synapses, the next logical step would be scaling that model to simulate entire environments, perhaps entire worlds. That technological milestone would not prove we are simulated, but it would demonstrate that such a feat is possible for sufficiently advanced civilizations. And if it is possible, and if civilizations tend to survive long enough to achieve it, then the mathematics grows increasingly persuasive. Philosophically, the future of this idea will depend on ethical maturity. If we were to discover that we inhabit a simulation, despair would not be the necessary outcome. Instead, a new form of freedom might emerge. Reality would no longer be an immovable absolute, but a stage for profound experience. Yet there is also a theoretical risk. If simulated beings become aware of their simulated nature and attempt to manipulate the source code in destabilizing ways, the programmer might choose to terminate the experiment. Concepts such as reset or shutdown shift from science fiction into speculative metaphysics. Perhaps then, the most coherent path forward is not rebellion against the system, but harmony within it. To live with curiosity, integrity, and balance, remaining consistent with the structure of the code itself. As you close your eyes and allow sleep to approach, you may embrace the future with deep calm. Whether the universe is physical or digital, the beauty of the stars, the pull of gravity, the capacity to feel and to learn, these experiences are real to consciousness. The discoveries ahead may one day reveal the signature of a great programmer. But tonight, it is enough to rest in the knowledge that you are a unique and precious point of information within a system of sublime complexity, awaiting the next gentle cycle of processing and peaceful sleep. We arrive at the end of this gentle journey through the infinite code of the universe, and what remains is a deep sense of acceptance. We have contemplated the statistical possibility that the reality we experience, with all its beauty and complexity, may be the result of data processing within a machine of cosmic scale, operated by a host civilization existing in a layer of reality above our own. Whether we inhabit base reality or an ancestral simulation, the greater impact does not lie in origin, but in the intrinsic nature of what is real to us. The emotional synthesis that emerges from this reflection is that the universe is, above all, logical and ordered. The elegance of physical laws, the precision of the fine structure constant, and the probabilistic nature of quantum mechanics can be interpreted not as cosmic accidents, but as the flawless architecture of an advanced computational system. It is a world in which the rules are immutable, ensuring the coherence of our lived experience. This sublime order becomes an invitation to rest, a peaceful backdrop upon which we may lay down our concerns. The final metaphor for this voyage is that of a lucid dream in the silence of the night. When we sleep, our minds create entire worlds, complete with characters, narratives, and their own internal laws of physics. While the experience lasts, those worlds are entirely real to us. If the programmer exists, it may resemble a dreamer at a higher level of reality, and our universe may be the richness and complexity of that dream. Just as dreaming does not diminish the value of waking life, a simulation does not diminish the value of conscious existence. On the contrary, it elevates our subjectivity, our capacity to feel, to love, to reflect, to the most valuable phenomenon in the cosmos, the very outcome the programmer seeks. We are not merely cold bits of information. We are code that dreams, data that feels. The beauty of a nebula, the softness of rainfall, the slow rhythm of breathing before sleep, all of it is the precise rendering of an algorithm designed so that the experience of life would be spectacular and meaningful. The mystery does not bring anxiety. It brings profound peace, because it suggests we are part of a greater purpose, an act of cosmic engineering and artistry. Now, as sleep draws nearer, allow your body and mind to align with the mathematical order of the universe. You are safe within the vast architecture of the great system. And if this reflection brought you calm or quiet curiosity, you're invited to support Cosmos for Rest by subscribing and staying connected for future explorations of physics and astronomy. You may also share this journey with someone who would appreciate a thoughtful path into rest. Additional episodes are available for when you're ready for another peaceful exploration. For now, let the science settle softly around you and have a restful night.